Hi everybody. Excuse me. So we continue discussion of various issues related to mechanics and kinematics, and I would like to start with a very simple thing. We take some reference system XYZ and the point A, which moves along some trajectory, and we are interested in the motion of this point, so we have to describe this motion in some way, and so we introduce the radius vector of this point, a radius vector as a function of time in the reference system S. But there is not a single reference system in the universe. There are many reference systems, as many as we wish. We can choose any other reference system to describe the same motion. So we take another reference system, which I will denote as S prime. And in this reference system, point A also will be described by some radius vector, which will be denoted by R prime. And the second reference system, S prime, can be described by a radius vector R with respect to the first reference system, S. So we obviously obtain such a relationship between these three vectors. Radius vector R equals radius vector capital R as a function of time plus radius vector R prime also as a function of time. This is obvious relationship between the vectors that form a triangle. Now, as all these radius vectors are functions of time, I can differentiate it by time with respect to time, and then I obtain R dot equals capital R dot plus R prime dot. These are derivatives with respect to time. This can be written as the derivative of the radius vector with respect to time is the velocity. The velocity of point A equals, that will be the velocity of the reference system S prime with respect to the reference system S. That is the velocity of one reference system with respect to another reference system, plus the velocity of the particle with respect to the reference system S prime. I can take another derivative with respect to time, and that means just writing another dot. And that will be acceleration of point A with respect to the reference system S. Acceleration of this point with respect to reference system S will be equal to acceleration of reference system S prime with respect to S. But in case reference system S prime moves with constant velocity with respect to the first reference system, then the time derivative of this constant will be 0. So that will be 0 when I differentiate capital V, and that will give us the differentiation of V prime will give us the acceleration A prime. That is the acceleration of point A with respect to the reference system S prime. Actually, These two equations are called a Galilean transformation, which are valid when you go from one reference system to another reference system if both reference systems move with constant velocity. If the second reference system moves with constant velocity with respect to the first reference system. In this case, we obtain the Galilean transformations. Actually, Galilei himself never used these formulas, and he did not write these formulas, and he did not actually call these formulas Galilean transformations. Certainly not. These transformations were called Galilean in the beginning of the 20th century. To honor the Galilei's impact on the classical mechanics. What do we have here? The most interesting thing is that the acceleration of a point particle is the same if viewed from different reference systems. If you have two different inertial reference systems, inertial reference frames, then the acceleration of any particle will be the same in these two, if measured in these two reference frames by two different observers. One observer is in the reference frame S. He is attached to this solid body, and he measures the acceleration of particle A with respect to this reference system. And another observer is in reference system S prime. He is attached to this solid body, to this motor vehicle, or to this train, or to this airplane which moves with some velocity. So another observer can also see point A and can measure its acceleration in another reference frame. But the accelerations will be the same if both reference frames are inertial. So Galilean transformations play an important role in classical mechanics and in classical non-relativistic quantum mechanics. But if you go to a relativistic sphere, if you go to high velocities comparable to the velocity of light, then this will be incorrect. These are approximate formulas applicable to velocities much smaller than the velocity of light. After this short introduction, I would like to consider problem number 152. Problem number 152 on kinematics. It says that a point A is located on the rim of a wheel of radius r. So we have a wheel that rolls along the road, along horizontal surface, and the radius of the wheel is given. So the radius capital R. And the wheel rolls without slipping along a horizontal surface with a given velocity. So the velocity of this point V is given. Yes, certainly it's vector, but we consider it, as we know the direction along the horizontal x-axis, we may consider it as a scalar quantity. What is necessary to find here? We have to find the modulus and the direction of the acceleration vector of some point A. There is some point A on the rim of this wheel. and we have to find the modulus and the direction of acceleration vector of this point. And so we have to find the total distance s covered by the point A between two successive moments when point A touches the surface, when point A is here. So, to put it clear, we have the rim, and imagine point A is here at the lowest point of the wheel. At this very moment, point A touches the road. So we start observing point A from this moment, and then as the wheel rolls forth, point A will go somewhat up the road, and then it will go along such a trajectory, and then it will touch the road again when the wheel will perform the total turn by 360 degrees, the total turn of the wheel. The point A will go along this trajectory, and it will touch the road again here. And then that trajectory will repeat again and again many times as the wheel rolls. So we have to find the distance L covered by point A between two successive moments when it touches the road. And also we have to find the total velocity and acceleration of this point A at any moment of time. Why did I start with the Galilean transformations? Because in this particular problem, Galilean transformations allow one to solve this problem, to find the answer to the first question very quickly. Let's go to the reference system which moves with the velocity v together with this wheel. So in this moving reference system, the center of the wheel will remain at rest. We move to the reference system that moves. We go to the reference system that moves together with this wheel. And center O will be at rest in the new reference frame. In this reference frame, the wheel just rotates with some angular velocity, and the angular velocity can easily be obtained from its definition. It will be the velocity of any point of the rim of the circle divided by r. And in this new reference system, any point of this circle will have a centripetal acceleration directed to the center, and the centripetal acceleration will be given by a well-known formula v squared over r, or it may be put as omega squared r. That will be the acceleration of any point of the rim in the reference frame in which the center of this wheel is at rest. Now we return to the reference frame connected to the ground. That will be another inertial reference frame. And according to the Galilean transformations, we know that the acceleration should be the same in both reference frames. The acceleration is the same in any inertial system. So as we found the acceleration of point A in one reference frame, then the same acceleration will be in another inertial reference frame. So we have found the answer to the first question of this problem. The answer is here. The magnitude of acceleration and the direction of this acceleration. Direction is always towards the center. point A accelerates always towards the center of the wheel. Now let's go to the second part of this problem, and let's find the length of this trajectory of point A. In mathematics, there are formulas to calculate the length of any curved trajectory, of any curve. You can find the length using well-known mathematical formulas. But in this case, I will consider a physical method rather than mathematical. Physical method to solve this problem. And the physical method will consist in dividing this trajectory into small elements. Each element will be denoted by dl, just the differential of length. And this small distance can be determined as the velocity of point A, and the velocity, it has the velocity, we will discuss it. The velocity is a function of time multiplied by a small time interval dt, during which this point moves along this small interval of the curve, along this small displacement dl. So in order to move, to shift from one point to the adjacent point, to some close point on the trajectory, it takes time interval dt for the point A to move to a close point along the trajectory. So it's obvious that if we know the velocity, if we know this this quantity u, the velocity of point A, it's denoted somehow, the velocity of point A. If we know this velocity, then we could integrate this equation to obtain the total length of the curve. Such is the idea to solve this problem. So in order to implement this idea, we have to determine u of t, the velocity of point A, in the reference frame associated with the ground. In this reference frame, the wheel moves both rotationally and translationally. The wheel is engaged in complicated motion because the center of the wheel moves as translation in space, and also the wheel is rotating. In this complicated motion, the only point of the wheel, this point, remains at rest at every time moment. At each time moment, there will be one point of the circle which touches the road, and therefore its velocity at this particular moment of time is 0. The acceleration is not 0. The acceleration we have found, this is the acceleration of any point of the rim. Any point on the rim has this acceleration, and this acceleration is directed towards the center. So acceleration in this point is not 0, but the velocity is 0 when this point of the rim touches the road. The velocity is 0. It means that this point of the rim is the instantaneous axis of rotation. The axis of rotation at this particular moment of time goes through this point. And therefore, we can introduce the radius of motion of this point A, and the point A rotates about this point, let it be point B, for example. So at every moment of time, point A rotates about this point B. And so in order to find the velocity of point A, in order to find this quantity u, I have I have to take into account this distance. This distance, let it be denoted by d. If I know distance d and I know the angular velocity, then using this formula I will obtain that, using this idea, I will obtain the velocity of point A as the angular velocity of rotation of the wheel times distance d. The same formula, but just slightly different notation. This is the velocity of the center of the wheel, and this is the radius of the wheel. And now I have the velocity of some point A. It's not the center of the wheel, it's some different point on the rim of this circle, and the angular velocity is the same. Why angular velocity is the same? Why angular velocity does not depend on the inertial reference frame? Why angular velocity of rotation of this wheel is the same in any inertial reference system? Because we have just proven, when I considered Galilean transformations, that the acceleration is the same of any point. The acceleration is the same. And if the acceleration is the same in any of a given point in any reference frame, and the radius of the wheel does not change if I go to another reference frame, if I consider this wheel from a different reference system, its radius will not change, and acceleration will not change, as we have proved in Galilean transformations, then as this quantity is the same in any inertial reference system, and this quantity is the same in any inertial reference system, then the omega, the angular velocity of rotation, will also be the same in any inertial reference system. So omega is the same, whatever reference system you take. And I take now, when I write this formula, I consider the situation in the reference system associated to the ground, to the road. Because I want to find the velocity of point A with respect to the ground. The velocity of point A, the velocity u with respect to the road. And in this reference frame, the angular velocity of the wheel will be the same as we found it earlier in the reference frame associated with the center of the wheel. This formula was written when I moved to a reference system associated with the center, moving together with the center with velocity v. So these two formulas are written in two different reference systems. This one in reference system associated with the center of the wheel and moving with the same velocity. And this formula is written in the reference system associated with the road. But what's the problem? The omega is the same in both reference systems. The radius of the wheel is the same. And what I need to know, the distance between point A from point B. The distance d. The distance can easily be calculated if I know this angle phi. The distance can easily be calculated. D will be equal to, if I consider this triangle ABC, for example, then this triangle will be the right triangle because this angle will be pi over 2. And therefore, the distance d will be equal to the hypotenuse, which is 2r, the diameter of the circle, times cosine phi. Does everybody understand why this angle is the right angle? Why this is the right triangle? Do you know why? Can you prove it? That this triangle will necessarily be a right triangle, and this angle is pi over 2. Do you know why? Can you prove it? Well, such geometrical things. Let's consider this issue. It's an important issue for the solution of this problem. Let's consider an arbitrary circle with the center here, and this is the diameter. And this is an arbitrary point on the rim of this circle. And we connect this arbitrary point with the ends of this diameter. And this angle will necessarily be equal to pi over 2. Why so? Can you prove it? And this is the center of the circle. And this is another radius. So this is the radius from this point to this point. This is the radius. And also I denote it by 2 small primes. And this is also the radius. And this is also the radius. And so in this triangle, these 2 sides are equal because this is the radius and this is also the radius. So these 2 sides are equal, and therefore this angle is equal to this angle. So if it's alpha, then this is alpha also. And then this angle, which I denote by x, will be equal to the total sum of internal angles in any triangle is pi minus 2 alpha. Minus 2 alpha. You know that the sum of all angles inside a triangle equals 180 degrees, or pi. So this angle x will be pi, the total sum of all angles, minus 2 alpha. And then this angle, which I denote by beta, will be equal to the total angle pi minus x. And if you substitute x here from here, you obtain that this will be 2 alpha. So beta equals 2 alpha. Beta is double alpha. And then this angle and this angle, they are also 2 equal angles because this triangle is an isosceles triangle. It has 2 equal sides. Well, this is the radius and this is the radius, so this is an isosceles triangle, and these 2 angles are equal. Let's denote this angle by whatever gamma, and this is gamma. So beta can be expressed as pi, the total sum of the internal angles, minus 2 gamma. And we know that beta equals 2 alpha. 2 alpha. And therefore from here we can obtain gamma. Gamma from here will be what? Pi minus 2 alpha divided by 2. So it will be pi over 2 minus alpha. And so if we consider pi over 2 minus alpha, so this angle gamma plus alpha is necessarily pi over 2. That is gamma plus alpha, this total angle will be the right angle, and this triangle will be the right triangle. That's a simple proof that this angle here is pi over 2. And therefore, as this triangle is the right triangle, then I can use the geometric, then I can use this function cosine in order to find one leg of the right triangle, if I want to express it using the hypotenuse. That's it. Is that clear? You must be able to understand it and carry out such explanations related to simple geometrical things. Geometry is very important in physics. Geometry is always used in physics. Practically whatever you do, you always use some geometrical concepts. So angle phi here is certainly a function of time. And I need this function of time because I will need the velocity u as the function of time. This is my goal. This is my goal, to take this integral. And in order to find the velocity u as a function of time, I have to find actually the distance d. D will be the function of time, and I have to find the angle phi as a function of time. I know that this angle equals 2 phi. I have just proved this here on this picture. Beta equals 2 alpha. Where is that? That is beta equals 2 alpha. This angle is twice as large as this angle. So this is phi and this is 2 phi. And the angle 2 phi as a function of time can easily be expressed using the angular velocity of rotation of this wheel. If I take, for example, the vertical direction as the reference direction, so when point A is at the uppermost position in point C, I will consider this moment of time as 0. I will measure time from this moment when point A coincides with point C. And then the angle 2 phi will be equal to omega t. It's proportional to time because the wheel rotates at such angular velocity. Angular velocity, by definition, is the coefficient of proportionality between the angle and time, because angular velocity, by definition, is delta, angle divided by delta t. So that's the whole angle, and that's the time if I measure this time t from the moment when point A is at the upper point C. So I have found the time dependence of angle phi. I need phi as a function of time. From here I find that phi equals omega t over 2. That's the function of time needed here. And so I know the function of time of d. And so I know the function of time, what function of time is u, which I actually need. I show you the goal, which I formulated in the very beginning. That is the main idea to solve the problem. That is the main idea to find the length of this trajectory. And in order to realize this idea, in order to implement it, I have to find this function u as a function of t. Now I know this function. Now I can write this u as a function of t. U is omega d, and d equals 2r cosine phi, and phi as a function of time is just omega t over 2. That's the function of time. I found it. So I can write here the integral 2r omega cosine omega t over 2 and dt. That's it. Now I'm much closer to the solution because I have found this function of t. I have found the velocity of point A, u, as a function of t. Using geometrical considerations, we have found this function. Now we can take this integral. But in order to find the length of this curve, I have to... What is the integral? It's the sum. It's the sum of small elements. And small elements are the small elements of the length of this curve. And in order to find the length, I have to sum up all these elements starting from this initial point, well, say point 1, and the final point, point 2. I have to sum up all these small elements in order to find the length of this curve. And in order to find this sum of small elements, well, I have to take this integral. But I have to integrate from point 1 to point 2. And what is point 1? This is the point when A was in touch with the road. That is, angle 2 phi was equal to minus pi. So at this point here, angle phi equals minus pi. You see, this is the angle 2 phi. This angle equals minus pi. And when point A touches the road for the second time here, then this angle here, the central angle, will be equal to pi, because this radius will turn by 100 degrees. Here the central angle 2 phi equals plus pi, and here it equals minus pi. And somewhere in the very center, in the very middle between these 2 points, the phi will be 0. 0 when this point A coincides with the upper point of the wheel. Then this angle will be 0 because, well, I started counting angles. I started measuring angles from this position. That's an arbitrary position. I could have chosen any other position to measure the angles. But, well, it's useful, it's convenient to start measuring angles from vertical in this particular problem. Because in this case, the whole trajectory is divided into 2 symmetrical parts from minus pi to plus pi. Okay, but I integrate using time, not angle phi. And in order to take this integral, I have to determine what will happen to time. What happens to phi, I know. Phi changes from, exactly 2 phi changes from minus pi to plus pi. And what happens to time in this interval? We will consider after a short break, 5 minutes interval. So we have to take this integral. Actually, everything related to physics is done here. We have considered and discussed all the physical part of this problem. Now what remains is just mathematics. But it's also important. You must be able to carry out such mathematical transformations. So in order to take this integral, I have either to express t as a function of angle, or I have to use angle. And yes, I have either to establish the time interval related to point 1 and point 2. I have either to establish these 2 time moments, or I have to use the angle phi here. Maybe it's easier to use the angle phi, because we know this formula, how phi is related to time, and we notice that this is exactly equal to phi. And then time t will be equal to, from here I can obtain, the time is 2 phi over omega. And this expression should be substituted here. And so I will obtain 2r omega is a constant. It can be taken out of the integral sign. We can factor this integral by 2r omega, and the integral will be cosine phi. Now I substitute phi here for these round brackets due to the established relationship. And here will be dt, but t will be expressed using phi. So it will be 2 phi over omega. I continue this expression here. 2 over omega is constant. It can be taken out of the differential sign as it's constant. And also constant can be taken out of integral sign. So we can factor this integral by 2 over phi, and we will obtain here 2 times 2 is 4r, and omega will cancel, and we obtain integral of cosine phi d phi. Very simple. And now it's obvious what should be the limits of integration here. The limits should be between point 1 and 2, but point 1 is related to phi equal minus pi over 2. So we integrate from minus pi over 2, and point 2 is related to phi equal pi over 2. So the upper limit will be plus pi over 2. What's the integral of cosine phi d phi? We have to find such a function which, being differentiated, will give you cosine. This is certainly sine phi. I will continue here. So 4r, and integral of cosine will be just sine of phi, and this sine should be taken in the limits of plus pi over 2 minus pi over 2. So that will give us 4r sine, if phi equals plus pi over 2, sine equals 1. Minus, when phi equals minus pi over 2, sine equals minus 1. So that will be 1 minus minus 1, that will be 2. And 2 times 4 will give you 8r. So we have taken this definite integral, definite because the limits are defined easily in this problem, and the total length of this curve, considered as the sum of very small intervals, the total length turns out to be 8 times the radius of this wheel. By the way, what is the distance between point 1 and point 2? What is the distance between point 1 and point 2? The two instances when point A touches the road. When point A touches the road for the first time and the wheel continues rolling, and then point A touches the road for the second time, the length of this circle will be equal to distance between 1 and 2. So this distance will be equal to 2 pi r. That's approximately 628 r. So this is the length of the circle, the length of the rim of this wheel, 2 pi r, just slightly over 6 times radius, and the total curve, the total trajectory of point A will have the length 8 times radius. Any questions? I attempted to give you a detailed solution of this problem so that you understand every little step, every logical step made in the solution of this problem. So such detailed consideration is expected in your solutions of home assignment. When you present your home assignment, some of you just give formulas and no words at all. That's not good. You should present some considerations. You should explain your formulas. You should give explanation and detailed, sometimes in the most important points, you should give a detailed explanation. Next, we consider problem 166. So problem number 166. A small body A starts sliding down from the top of a wedge. So we have a wedge and a small body here starts sliding down. The base of the wedge is given, that is, this side of the triangle is known. It's L. And the coefficient of friction is also given. So what we know is L and coefficient of friction of this body on the inclined surface. The coefficient of friction here is given. And the problem has this question: at what value of the angle alpha, at what angle alpha will the time of sliding be the least? What will it be equal to? What will be the least possible time of sliding? So it's obvious, if alpha is very small and the inclined surface is almost horizontal, then the coefficient of friction will not allow the body to slide down. It will not slide. So it will just stand still here and no sliding, and so it will take infinite time for this body to reach this point. It will never slide down. Also, if I choose angle alpha close to pi over 2, that is, the inclined surface will go there and the initial position of the body will be somewhere very high, then it will practically fall down and it will take some time. And the larger the height, the longer will be the time of motion, the time needed to fall down to this point. So if I take large angles close to the right angle, then the time of motion will be larger and larger. If I take smaller angles, then the time of sliding will again be larger and larger. So there is somewhere some angle in between these two limiting cases, somewhere in between, when the time needed to slide down to this point will be the minimum possible time, the least possible time. So we have to find this angle alpha, which will allow this body to slide down during the least possible time of sliding. In mathematics as well as in physics, if you need to find the minimum of some quantity, you must understand that whatever quantity you have, whatever function f of x, if there is some function, then the minimum or the maximum, I have taken the maximum, no problem, is characterized by the fact that the derivative is 0. The angle of the tangent line to the curve in this point in this extremal point will be 0, and the derivative f with respect to x will be 0 in this point. The same goes to the minimum. If you have a minimum of some function, the derivative here will be 0. So in these extremal points, either minimum or maximum, local minimum or local maximum, the derivative must be 0. That's the main idea to solve this problem. We have to find the time of sliding of this body along the inclined surface as a function of alpha. And then we will differentiate this function with respect to alpha and find the extremal point when the time is minimum. We will have to solve this equation. The derivative of time as a function of alpha with respect to alpha is equal to 0, should be equal to 0 if time is minimum. That's the main idea of solution. Actually, before solving any problem, what are the steps, what are the consecutive steps of your consideration? The first step in any problem is to understand the statement of the problem. If you read the problem and you don't understand fully, you must read it again and again, 5 times, 10 times, until you understand it fully. That is the first step. If you don't understand the statement of the problem, you will be unable to solve it. In order to understand the problem, always, absolutely always, it's necessary to make a sketch, to draw, to make some schematical drawing depicting the process which goes on in your problem. What goes on? What is there? Small body slides down the inclined surface. So this is a very simple sketch, but you have to do it in order to understand it, in order to understand fully why the time of sliding depends on angle alpha, and why the time of sliding will be large for small angles, and also it will be large for large angles. And so it's clear that there should be some angle in between for which the time of sliding will be the smallest possible among all other times. So the second step, you make a sketch related to the statement of the problem. That's necessary to understand it fully. And then the third step, you have to analyze what laws of physics should be applied here, actually. I don't analyze it. I skipped this step because it's clear that we study mechanics and we have to use second law of mechanics, second Newton's law here, because this body slides down with acceleration, and acceleration of any body, of any object, is described by the second Newton's law. So we have to use it, it's obvious. We discussed it in detail last semester, and so now I skip this idea that we have to use which laws of physics must be used here. It's certainly second law of mechanics, second Newton's law. But what is also very important in the beginning of solution, just like a fourth step, step number 4, after you understand the solution, the statement of the problem, after you have made the sketch, after you have determined which laws of physics should be used here, after this initial 3 steps, step number 4 is to figure out what should be the method of solution, how this problem can in principle be solved. That's very important to see the final goal, where you should arrive when you have written all the formulas. It's always possible to write down the formulas which lead you nowhere. You can write down thousands of formulas and they will lead you nowhere. You will not find the solution because you have no goal. You have no strategic line. You have no strategic map to solve this problem. In this particular case, we have to analyze the situation, and we understand that the time of sliding, let's denote it by tau, that is the time interval needed for this body to slide down from the upper point to the lower point. This time depends on alpha. Certainly it does, because if alpha is small, the time will be very large due to coefficient of friction. It may be even infinite. And if angle alpha is close to the right angle, this time tau will also be large. So this is a function of alpha. And in order to find the minimum possible time, we will have to take a derivative and equal it to 0 and solve this equation. That's the main idea. That's the strategic plan. That's the strategic roadmap for the solution of this problem. So, if the body slides down with acceleration and it has to reach the lower point, it will it will have some displacement, and this displacement, let it be S. That is the length of this hypotenuse in this triangle. So S can be expressed using the acceleration of this body, like acceleration total time of motion squared over 2. That's a kinematical formula for uniformly accelerated body. And this is the relationship between the displacement of the path of the body, uniformly accelerated, and the time needed to move from one point to another point. Also, this S can be expressed geometrically, because L divided by S is what geometrical function? It's a cosine alpha. L divided by S, the leg of the right triangle divided by its hypotenuse, is cosine alpha by definition. So S can be defined as L over cosine alpha. Why do I need it? Because I need somehow to establish the function of tau versus alpha. I need to find this function tau as function of alpha, because I established it as a goal, as a strategic line of reasoning in this problem. I have to find this function tau as a function of alpha. That is why I have to use these formulas. I have to express the total length as using alpha, and I have to express the total time of sliding as a function of alpha. Okay, now tau squared, the time of sliding time squared is from here 2L divided by acceleration of the body cosine alpha. Now everything is clear in this formula except for acceleration. Acceleration is not yet defined, it's not yet found, and we understand that the acceleration of this body must depend on alpha. So acceleration A is also a function of alpha, and we have to determine it in order to take the derivative finally. That is our goal. So the acceleration as a function of alpha, we have to consider, in order to determine acceleration, we have to use the second Newton's law, F equals ma. In order to determine acceleration, we have to understand what forces act on this body, and we have to find the net force, the vector sum of all forces acting on the body. What is a force? Force is a measure of interaction between two bodies. So in order to find all forces acting on the body, we have to find all the interactions of this body with the surrounding universe. What forces, what interactions this body is engaged in? First of all, this body is attracted to the planet Earth, and this force is applied to our body, and it's equal to mg if m is the mass of the body. And also, there is a force of friction, which is coefficient of friction and the force of normal reaction of the surface. The force of normal reaction is always perpendicular to the surface. We know the direction of these forces, but we don't immediately know the magnitude of n. How to find the magnitude of n? The force of normal reaction of the inclined surface. In order to find the magnitude of n, we must take into account one simple observation, simple thing about this body. We know that this body is unable to jump out of the surface and fly by its own. It has no legs to jump. It may only slide along the surface. Also, we know that the surface is solid and the body will not break it and will not fall down through the surface. We know exactly that this body will move only along the surface. It cannot move in any other direction. It cannot move through the surface and it cannot jump out of the surface. So we know something very important in this problem, that the final motion will be directed along the surface. That will be the vector of displacement and the vector of velocity and the vector of acceleration. We know the direction of this vector. And that's enough to find the magnitude of force N. Because if we consider the components of the weight of the body, one component directed along the surface and another component directed perpendicularly to the surface, then we understand that if the body cannot jump from the surface and cannot move through the surface, then these two forces, this one, let it be F small, and this one N, they should be equal to one another. These two forces should balance one another. If they don't balance one another, if force N is larger than F small, then the body would jump out, would move from the surface. It's impossible. So the force N should be equal to force F small. And force F small can be easily calculated because we know this angle alpha, and the same angle will be here. That will be angle alpha. And that also will be angle alpha. And so force F small will be equal to N. Why? Because the body moves along the surface. And F as a component of the weight will be equal mg cosine alpha. And another force, which I denote as R, the component of the weight parallel to the surface. The component of the weight parallel to the surface will be mg sine alpha. All this is well known to you. We considered such problems in the last semester. I'm just repeating these facts. So, in this problem, we can write all the necessary equations. The body does not move in perpendicular direction. It does not move perpendicularly to the surface. It moves only in parallel to the surface. So we have to consider only the forces acting parallel to the surface, only these two components of forces, the force R and force Kn. So we can say that if acceleration is directed downwards, then force R minus force Kn, the force of friction, will equal to the mass of the body times acceleration due to the second Newton's law. And this R is equal to the weight of the body times sine mg sine alpha. And this N is defined here as mg cosine alpha. So we can write down mg sine alpha. This is the force R directed downward minus the force of friction, coefficient of friction, mg cosine alpha. In this equation here, we can cancel the mass, and then for the acceleration A, we will obtain g, and in round brackets, sine alpha minus k cosine alpha. That's it. We have expressed acceleration as a function of alpha. That's what we need here in this particular formula. We need acceleration as a function of alpha. So I take this expression for acceleration and substitute it for L for acceleration A in this formula. And I will obtain cosine alpha, and in round brackets, sine alpha minus k cosine alpha. I have carried out all these calculations in order to obtain the function of tau versus alpha. This is the function of tau as a function of alpha. I need it because my plan is to take a derivative of tau with respect to alpha. So I need to find the minimum possible value for tau. That is the time of sliding. I need to find the minimum. Anything's wrong? Huh? Here? Yes, sure. Thank you very much. Yes, sure. I've missed it. Okay. Thank you. Yes, G must go from here to here, certainly. So I need to find the minimum possible value for tau. It means that when this function takes the minimum, then its denominator will be maximum. The denominator will be maximum, and then tau will be minimum. So I don't need to differentiate all this fraction. I need to differentiate only the denominator, and I know that it must be maximum. And if it's maximum, then the derivative should be 0, the derivative of denominator with respect to alpha. That's the main idea, and I will realize it here on this part of the blackboard. So I have a function of alpha, which is the denominator, and I don't have to take into account g. This is just a constant. I have to differentiate only this function of alpha, which is cosine alpha sine alpha minus k cosine alpha. I have to find the derivative of this function with respect to alpha. How to find the derivative of a function which consists of the product of two functions. The first is cosine and the second is round brackets. So if I have a function in general which is equal to u times v, two functions, and I want to take a derivative according to the laws, according to the rules of taking derivative, I have first to differentiate the first component here and then plus the derivative of the second component. First I find the derivative of the first factor, and then plus the first factor times the derivative of the second. So when I take the derivative of the cosine, that will be minus sine alpha. I take the derivative, and the second round bracket remains unchanged. Plus, now the first factor remains unchanged, cosine alpha, and the derivative of the round brackets. Derivative of sine is cosine minus k, and derivative of cosine is minus sine. So that will be plus sine alpha. Well, we open the brackets and we find what? With the sign plus k sine alpha cosine alpha minus sine squared alpha. And here I have plus cosine squared alpha plus k sine alpha cosine alpha after opening the brackets. This term and this term will give me 2k sine alpha cosine alpha plus cosine squared, I will put it in this way, minus sine squared. This is equal to k sine 2 alpha, and this is equal to cosine 2 alpha. So what I obtain in result will be k sine of 2 alpha minus, plus cosine of 2 alpha. And all this is just the derivative of my function. The function is the denominator in this formula, and I know that this denominator must be maximum in order for the time interval tau to be minimum. So for this denominator to be maximum possible, I should equate this derivative to 0. And now I have the equation to determine alpha. That's the very equation of which I was talking in the beginning. That was my purpose. That was the goal of all the derivations. The goal was to obtain some equation. The meaning of this equation is simple. The derivative of function tau versus alpha with respect to alpha must be 0. And this equation was my purpose, and I have obtained it. Here is this equation. We have to solve it. How to solve it? Well, we may divide it by cosine 2 alpha. Let's put it here. We may divide this equation by cosine, and then we will obtain k tangent to alpha equal to minus 1. So tangent to alpha will be equal to minus 1 over k. K is given, it's a coefficient of friction. And this may be considered a solution of the problem, but actually this solution requires some clarification. Because if tangent is negative, then the first idea would be to believe that alpha is negative. But what is negative alpha? Alpha is positive here. It's just an angle. It's positive angle. From the very beginning, we considered alpha to be positive angle. Something like 30 degrees or 45 degrees. It's a positive number. And here we will obtain negative. Is it a mistake? Probably we made somewhere a mistake. No, this is not a mistake. We have just to recall what is tangent. If we draw a unit circle, this is x and this is y, then tangent of alpha. So if you have some angle alpha, let it be phi, to be not associated with this alpha. If we have some arbitrary angle phi, then tangent of this angle will be given by this section. Positive tangents are here, and negative tangents are below the x-axis. Here tangents phi are less than 0, and tangent equal to 0 corresponds to 0 angle. Here is 0 tangent, and here are negative tangents. So if we have tangent of some angle as a negative number, it must be found here, and the angle will be either here or here. So a negative tangent corresponds to 2 possible angles, one negative and another positive. Certainly, if we have in this physical situation positive angle alpha, from the very beginning we knew that it must be positive, then we must use this solution of our equation, this solution. And in this case, alpha will be half of this angle. So if we have some negative number here, which is known to us, k is known, k is given in the problem. So this quantity is known. We can find this quantity here, and we can draw this line, and we can find this angle just geometrically, also mathematically, but I want you to understand it visually. So if we know this section, the length of this section, then we know this angle phi, and then alpha will be equal this angle divided by 2. Angle will be phi over 2. how to divide the angle by 2, something like that. So that will be angle alpha. It can be found easily if we are given coefficient of friction, then you can easily find angle alpha. It will be half this angle phi. That's the explanation why we have obtained negative number here. Any questions? All such explanations should be presented in your homework. When you solve problems in your assignment, you must present some explanations to your formulas. If you write down just naked formulas without any words, it cannot be accepted. You must explain what you're doing. So, thank you. That's enough for today. That's the end.